So, hello everybody. Thank you for coming at this in early morning. So my name is Joël Bensoam and I come from IRCAM. IRCAM is an institute in the middle of Paris near the center of Pompidou who makes musicians and scientific. And as such, I'm working in the instrumental acoustic team, so I'm not a musician, a mathematician, but I try to model mostly how propagations of waves in instruments and try to model this sort of things to make simulations for musicians. And so I was really interested in geometric mechanics to find to contribute and do something to modelize nonlinear propagations of waves for example, in this sort of systems. To model the string vibration with the large displacements, it could be a good idea to use geometric mechanics. And so this is a simple example. So you can imagine that you want to describe the motion of a beam. The model came from Reisner or Khosra. Khosra, the brother Khosra, made this sort of models. And the thing is that you have two independent variables, the times and also the arc lengths. So the motion of the beams is described as a surface in configurations and space of configurations, and this space of configurations is, in this example, the special Euclidean groups, that is to say, combinations of rotations and translations. And the main question for us is what are the equation of motion of this type of models? And secondly, how can we apply the Noether theorems, and if there is something that leave this system invariance? As you can see, it's invariance through the action of the group SUE3. So what happens when we apply the Noether theorems according to the fact that we have now more than one variables? So this is the main question I would like to introduce in this first talk. So maybe. Where is my? So, if you are not a mathematician and you try to go in geometric mechanics, you have to face this sort of descriptions. And for people who are not mathematicians, this description is really hard to understand. For you it's something really evident, but even from Marsden, in the end of the last centuries, he described the fact that some canonical one form came from the Hamiltonian part of the system. Then you have to make a Legendre transform of an inverse Legendre transforms, and for him it seems that this sort of things came from nowhere, and as you can see historically, the fact that Lagrange do his first works and also historically, it seems that the things are reversed in these formulations. So I will try to make a sort of historical constructions of all these things, and we will see how it will happen when we have now more than one independent variables. So let's go back to, so I can make a drawing somewhere. Okay, okay. So let's go back to something that Cartan writes in the 1930, and so to explain the Hamilton principles and the symplectic forms, he tried to figure out the things with let's say almost 7 variables, something for the time, something for the positions. So it's 3 variables and something for the velocities. So you can imagine that is a sketch, that a trajectory is curves in this sort of space. Then he will apply a variation of these curves in arbitrary directions. And he tried to compute the variation of actions due to this variation of these curves. So he obtains 2 terms, and you are perfectly, you know all these things. One on the boundary. You can also change the boundary in here from time t and time t epsilon, which is not exactly the same. So you have two terms, and if you choose vectors variations that is vanishing on the boundaries, then you obtain the well-known Euler-Lagrange equation of motions. But he noticed that if you now choose a curve that is a solution of the Euler-Lagrange equations, and he choose a variation with boundary, with something that varying on the boundary, then the variation of actions is described by these terms. And so you have here the new variables, the momenta, and here you can define new functions, which is the Lagrange transform of the system. So in this way of thinking, the momenta and the Lagrange transforms appear really naturally. Then he tried to figure out several real trajectory that are solution to the Euler-Lagrange equations, and he noticed that the integral over collections of curves of the Poincaré-Cartan theta, these terms does not depend on the choice of the tube of real trajectories, and then you can compute the fact that it's an invariant. X is the vector along the trajectories. The fact that the curve is how do you say that? It's a closed curve, then this term is 0. Then you have to introduce the pre-symplectic forms coming from the Poincaré-Cartan forms. And as you can see, you have two terms, something which depend on the positions and the momenta of the differential of these things, and something which depend on the Hamiltonian functions and the time. And when you apply the fact that along the trajectory the symplectic forms is conserve two forms, then he will find again the Hamilton canonical equations. You can also try to introduce a symplectic structure, which is a canonical symplectic structure depending only on the positions and the momenta. Then you will have this sort of things which come from this equation. This is exactly the same. You move the Hamiltonian parts through the right part of the equations. So if you introduce now the Poisson bracket by the fact that with this sort of thing, then you can have the Poisson equations, which is exactly another way of saying the same things. And you can also introduce the conserved quantity, saying that the conserved quantity has a vanishing Poisson bracket with the Hamiltonian functions. So it's for me, I have to learn about all these things, but the main important things is that we have to do something with more than one variables, t and variable corresponding to the time and variables corresponding to space, for example. And we will have to do exactly the same things, and considering some variable, in applying the Hamilton principles, we will have to do something to consider that we can add some variable boundary conditions. Then we will have to take care of the holonomicity of the things, trying to use the contact forms. And doing that, we will have a symplectic forms, and Hamiltonian formalism will arrive naturally. So, I will try to do this now. So, you can imagine now that we have not here just one variables, but we can have many variables. So, with mu, for example, x1, x2, xn. And so this part of the configuration space is written by and is figured out or described by y coordinates. And again, you can have some many variables for the configuration space, and this part is all the derivative all of the derivative of the configuration space by the independent variables. So the principle, the Hamilton principles, is now a map between the set of all the sections. It means that for each variables composing to the time or space, you can have en bas in the, well, forget about it. So for each sections, you can compute the variation of an action, the action. And now you want to do exactly the same thing, trying to make the section variate and to compute the variation of actions. And if you do exactly the same things, and it's even a little bit more complicated, but you have also two terms. A terms on the boundary and a terms that will give you the Euler Lagrange equations, but with many variables. And doing that, you have to introduce a Poincaré-Cartan n+1 forms. It's not, n is the number of spatial variables. When the n was 0, you have just the one forms. Maybe we can go back to this these things in here. This was the Poincaré-Cartan forms. So it's a one form, and now we will have n+1 forms with a generalized momenta in here and a generalized functions corresponding to not function again this an Hamiltonian versions of and Frédéric, it's not a function. It's also forms like the Lagrangian density. Well, it's a density in here. Okay, so it's a function. This part is the density, so this is also functions, and now we have momenta exactly. But momenta with which is now given by also many subscribers. So to do that, we have to take into account the contact forms, saying that when we make a variation of sections in this one jet formulation, then we want to move from a section to another one, but with the fact that we want to conserve the holomicity. The fact that when we lift the section from this plane to with the derivative, then we have to say that the height of this part corresponds to the derivative of the curves of the sections. So it's a little bit technically complicated, but to do that, if you choose any vector fields to make a variation of sections, then to conserve the holomicity, you will have something to conditions given by this terms in the third directions. So again, you can consider that you will choose a vector of variations that vanish on the boundary. Then you will obtain the Euler Lagrange equation, but with more than one variable. So you will have some partial derivative equation now with mu, the number of independent variables. So you can write also an Euler Lagrange one forms. And if you choose to consider, well, so after that you can also do exactly the same thing with the Poincaré-Cartan forms, and if you make the derivative of this Poincaré n+n forms, n+1 forms, then you will obtain a multisympletic form, and the fact that with one variables you have a conservation of the symplectic forms is traduced now with the variation theorem, saying that for any vector fields given to this multisymplectic forms, and the fact that you pull back by a section which is a critical section, then you will have evaluation terms. So the important things now is how can we apply the Noether theorems, saying that if you have a natural symmetry, something that leaves the Lagrangian invariance, like this, what is the things which will be, well, what is the moment map, the thing that will be constant on the critical sections. So you can compute this moment map just by giving the symmetrical natural symmetry to the Poincaré Cartan form, n+1 forms. And it's easy, really easy, to show that this thing is a conserved things along the critical sections. You just start from the fact that the Poincaré Cartan n+1 forms is also invariant along the symmetric field, and if you make the direct calculation, then you will find that this thing is invariant along the critical sections. So in to make a summary, we just introduce many variables, more than one independent variables. We make a variation to conserve the homomorphicity of the sections in computing the variation of actions. Then we have obtained a Poincaré Cartan form. And if we want to apply the Noether theorems, we just give the symmetric field to this Poincaré Cartan form to obtain the moment map. So this is the symmetry, the summary of my things. And now, what happens if this configuration space is a symmetric group also, if it's a Lie group? So what happens to the Lagrange equations, and two, what will happen on the conserved momentum map associated to the symmetry given by the symmetric field given by the Lie groups? So we'll do exactly the same things, but this time instead of considering the derivative, we consider the Lie algebra of this sort of thing. So we move the velocity from a point in the group through the identity. You know well all these things. So we introduce the Poincaré-Cartan form to do that. So the velocity at the identity is the velocity somewhere in the group given to this Poincaré-Cartan forms. So again, we can have a contact form to traduce the holonomicity of the sections. So we can do exactly the same things. And to do that, we need to take variations when we compute the variation of actions in the Hamilton principles. Then we have to variate all the sections, And this times we have also a new terms that appears in the variation to conserve the homonomicity of the sections. So if we do exactly the same thing with reduced Lagrangian forms, reduce means that we use now the velocity according to the Lie algebra, then we'll have to introduce a Lagrangian Poincaré Cartan n+1 forms, which is expressed by the Moré-Cartan forms, and we will have also density of energy corresponding a reduced Hamiltonian density of energy. And again, we have two terms, the terms on the boundary and terms that will give us the Euler-Poincaré Cartan form, Euler-Poincaré equations. Maybe, well. So, it's because we have now more than one variables, we have partial differential equations, and because the Lie group is a configuration group, we have an adjoint terms that appears in the Euler-Poincaré equations. And now the question is, so what is the multisympletic form corresponding to these situations? Again, we compute this multisympletic form by the derivative of the Poincaré Cartan n+1 forms. And you have also a term corresponding to the fact that the Lie group is not automatically how do you say that? Well, forget it. And we can also apply the variation theorems. It's exactly the same. And now, to answer the question, what happens when we apply the Noether theorems? If we have a symmetric field that leave the system invariant, then we can compute the infinitesimal generator of this vector field. And it appears that if you, the things to understand, if you have a left, for example, a left invariance of the systems, then the invariant vector field, the right invariant vector field, will be the symmetric field. So there is a connection with the adjoint function between left and right velocity. And if we apply, if we compute the moment maps, that is to say that we give this invariant symmetric fields to the Poincaré Cartan n+1 form, then we will obtain a Noether current. This time it's not a function, it's a current. And it's really easy to compute it. And the result is that if you have in this left invariant configuration space for this part, then you will have a right symmetric fields that leave the system invariance. And the moment map is simply the momenta associated to the momenta associated to the right velocity. So, and as you can see, if we compute these things, the fact that this moment map, this current is conserved along the critical sections corresponds to this type of equations. That means that we have now divergence relations corresponding to the fact that we have several partial derivatives in these equations. So this I think I have time now for some questions, and maybe Frédéric, you can add some comment on historical things, and yeah. So.
You know, it's much better than getting.
Sorry?
It's much better than a lot of books about
You mean you thank you. Thank you. So I've just tried to do my best to understand what Cartan have done and to do the same thing in different situations. Thank you. So I think it could help for people to understand the multisympletic formulations.
You have computed this equation for your use cases for the group acting.
Yes. I can maybe I can show you for the beam. Not this one. So for this type of, so to be concrete, we can describe this sort of system. So a motion of the beam is a surface in configuration in the configuration space, which is SE3, a concatenation of rotations matrix and R3. So if we introduce, so H is an element of the group with two components, a rotation matrix and a vector of translations. So we can compute the derivative along times and along space. Space is given by the S coordinate. And we move back this velocity to the element, to the unity. So we have two velocity. In fact, a deformations corresponding to the fact that you make a derivative according to space, and we have deformation information in this part of the derivative, and you have velocity because now you have a derivative according to the times. To compute the Hamilton principle, you will need an energy actions. So you introduce the velocities and the energy, the kinetic energy, and the potential energy. So you have two matrices, you see, which is the moment of inertia. You have to compute the kinetic energy. You have you have a matrix of inertia, and in here you have the Hooke matrix. So you make the assumption that the energy with deformations is a linear correspondence. There is not. So you can compute in this situation a density corresponding to the kinetic energy and the potential energy. And now, if you apply the Hamilton principle, you have two variables, S and T. If you do all these things, as you can see, the group S, the special Euclidean group, is acting on these systems. Then you can apply the Euler-Poincaré equations, and so you have a sort of equilibrium between in inertia terms and potential or something that corresponds to deformation terms. Here, P and sigma is just the momenta associated to deformations and also to velocities. Maybe I have some like this. So the momenta is related to the velocities through the inertia moment matrix, and this is the constraint, the strain. No, this is the strain, and this is the comment on appelle ça? The force, and it's related by the Hooke matrix. So here are the equation of motions, and as you can see, it's a partial derivative equations, and you have two terms considering that the group is a non-commutative group. So you have adjoint terms corresponding to velocity and deformation in here. But you can also have a compatibility conditions. That means that if you make the spatial derivative of the velocity or the time derivative of the deformations, then something will you have something in here, and it's really known at the fact that there is a vanishing curvature of the connections. So okay, so you have two equations, and we will see it in the talk of Frédéric Hellin, that we will use these equations, and you can do exactly the same things on the right, corresponding to the fact that now you move the velocity and the deformation by multiplying by the inverse on the right in here. So you can have a right velocity and right deformation, right velocity, right deformations. And this time, applying the Euler-Poincaré equation, you will obtain directly the conservation law in here. So this is exactly the Northern theorems that appears in here. And you will also have the compatibility conditions in the same terms. And maybe François Gebalmas, I don't know if he's here, will say something about the numerical solution of this type of equations. We are trying to do something on this thing. More question?
More question? Okay. Thank you.